Yes, mathematics students. So we are now on our first lesson for the quarantine. Um, our lesson for this day is on the finding the relative extrema of a given function with the use of the first derivative test. So let's say we have the graph of this. This is a function, and this graph is going up infinitely and also going down infinitely to the right. So we know that there is no maximum value nor minimum value for this graph because again, this graph is going up infinitely and going down infinitely. So what we actually want to find out here are what we call the relative extrema or relative maximum and relative minimum. What do we mean by relative maximum, relative minimum? So if you would look at this part here, so this one here is the minimum relative to all these parts of this graph. While on the other side, this is the relative maximum on this part of the graph. So what we are actually looking at here is at what values, what x and y values of the graph, does the graph change from being decreasing and goes into an increasing pattern or from an increasing to a decreasing pattern. So with that, what we need to use is the relative extrema or the using the first derivative test. So to be able to determine the relative maxima or minima of a given function, these are the steps that you need to do. So first, you need to find the first derivative of the function. Now, this would be quite easy because almost all of the functions that we are going to use are polynomial functions. And the second part, or the second step, is to equate the first derivative to 0 and then we solve for x. So we use the usual processes. If we get a linear, quadratic, even cubic function, we just use the previous knowledge that we have from algebra in finding the values of x. And the answer or the solution to that equation are what we call the critical points. The third step is to determine open intervals in the entire number line, in the entire real number line. Open intervals basically not including the critical points. We will be able to see much more specific examples later on what these are. And then the fourth is the actual first derivative test. In the first derivative test, we will create here a table which contains three columns. Again, we will be able to see this clearly later on. Basically, what we want to find out in the first derivative test is if the function is increasing or decreasing. The critical points are where are the candidates for the relative maximum or minimum. So if a function is initially increasing, then went into a decreasing pattern, then what we have is a relative maximum. So basically we start from increasing and then it went decreasing. So this part here, the highest peak is what we call the relative maximum. And if on the other hand, it comes from a decreasing pattern and then went to increasing, so we have here a relative minimum. So the first derivative test here again is determining if the function is increasing or decreasing. And then if there is an alternating pattern, then we are able to get a relative maximum or minimum. And then the fifth step is to get the actual coordinate of these relative maximum or minimum. So the x value, the abscissa, is already the x values that we get from step 2 or the critical points. So what we now need to do here is just to solve for the y value, the ordinate, so that we will have our ordered pair and get the actual coordinate of these points. Some examples. So let's say we have the function f of x is equal to negative 3x squared plus 4x minus 5. So again, the first step is to find the first derivative. Of course, the first derivative is negative 6x plus 4. Second step, we will equate this to 0, negative 6x plus 4. So of course, transpose 4 divided by negative 6. So we get the critical point 2/3. So the third step is to determine the open intervals that do not include the point 2/3. So we will start from negative infinity up to positive infinity, but have a break at 2/3. So if we would have the number line, so from negative infinity to positive infinity, so we have 2/3 right about here, there. So the intervals that we have are those that are to the left or lesser than 2/3, and those to the right of 2/3, or those that are greater than 2/3. So that's the first interval, and that's the second interval. And in notation, it is this. So we have from negative infinity to 2/3 open, and also 2/3 to positive infinity also open. So those are the intervals that we want. So the fourth step is the first derivative test. So again, we will make a table with 3 columns. So the first column is the interval, the second column is the test point, and third column is the sign. So once you have the intervals, what you need now to do is choose a test point that is contained in that interval. Usually what we choose are the either the greatest or least integer closest to the test point. So for this case here, from negative infinity to 2/3, again, these are all the numbers that are less than 2/3. The most convenient number that we can choose, or the test point, is 0. And then for the interval 2/3 to positive infinity, again, these are the numbers that are greater than 2/3. The most convenient number to use is 1. Now remember, our first derivative was negative 6x plus 4. So if we substitute 0 to negative 6x plus 4, this will be 0 plus 4, so that's positive. And if we substitute 1 here, so we will get negative 6 plus 4, so that is a negative. So the fifth step that we need to do is to substitute the critical point to the original function. So we are looking for f of 2/3. So we'll have negative 3, and this times the square of 2/3 plus 4 times 2/3 minus 5. Of course, the square of 2/3 is 4 over 9. And then simplifying everything, we get negative 11 over 3. Okay, so because we had from increasing to decreasing, so what we have is a relative maximum. And the coordinate of that relative maximum, where did the change from increasing to decreasing happen? The x value is 2/3, the y value is negative 11 over 3. So if you look at the graph, it would be something like this. So from increasing, it went on to decreasing. So this one, it's pointing at the relative maximum. So this is the relative maximum. Okay, next example. Find the relative maximum or minimum, or again, plural will be maxima or minima of the function negative x cubed minus 5 halves x squared plus 2x plus 1. So again, the first step is to find the first derivative. So of course, the derivative of negative x cubed is negative 3x squared. Derivative of negative 5 halves x squared is negative 5x. Derivative of 2x is 2. And derivative of 1 is 0. Equate that to 0. We have here a quadratic equation. And this one can be factored into negative 3x plus 1 times x plus 2. So remember, if this is equated to 0. So we get a solution if this is equal to 0 or this is equal to 0. So we equate both factors to 0, and then we can solve simultaneously for x. So we will get x equal to, um, this should be, yeah, negative 3x is equal to negative 1. So x is equal to positive 1/3, and x is equal to negative 2. Okay, so what are our intervals? So negative 2, of course, is less than 1/3. So we put negative 2 on the left first so that we will not get confused. We start with the lower values. Okay, so negative 2, that's that point. And positive 1/3 would be around this point. So if you would see, we actually divided the number line into 3 intervals. So we have this interval here to the left of negative 2. We have the interval between negative 2 and positive 1/3. And we have the interval to the right of 1/3. So those are our intervals. So that's from negative infinity to negative 2. Negative 2 to positive 1/3, and positive 1/3 to infinity. Okay, so again, the fourth step is the first derivative test. So our intervals are here, and the greatest number that is less than negative 2, or the greatest integer less than negative 2, is negative 3. The most convenient number to use if we have an interval that is from a negative number to a positive number, we try to always use 0 because that's always convenient. And then from 1/3 to positive infinity, the greatest number, or the least integer greater than 1/3, is positive 1. So again, if we substitute negative 3 to the first derivative, what we will be getting is a negative value. If we substitute 0, then we will get a positive value. And if we substitute 1, then we will get a negative value. So again, we see here an alternating pattern. So decreasing, increasing, decreasing. So the next point, the next thing that we need to do is to evaluate the critical points into the original function. So we will have f of negative 2, so that's the negative of negative 2 cube, minus 5/2 times the square of negative 2 plus 2 times negative 2 plus 1. Now please take note that we are cubing here negative 2. So negative 2 times negative 2, that's positive 4 times negative 2, so we get negative 8. And of course, the square of negative 2 is positive 4, and so on. So the negative of negative 8, that's positive 8. And then 5/2 of 4, that's 10. 2 times negative 2, that's minus 4 plus 1. So we get negative 5. So remember, we need to evaluate both critical points. So we also evaluate 1/3. So the cube of 1/3, of course, is 1/27. The square is 1/9. And simplifying everything. By the way, I just used here the least common multiple or least common denominator process. So least common multiple of 27, 18, and 3 is 54. So the final value that we get is 73/54. So again, what we had was an increasing, decreasing, no, sorry, we went from decreasing to increasing and then back to decreasing again. So we have a relative minimum at negative 2, negative 5. Again, this is the x value, this is the y value, and the relative maximum at 1/3 and 73/54. So if we look at the graph, it's a bit like this. So we have at negative 2 and then negative 5, and then 1/3 somewhere around here, and this is roughly 73/54. So these are our relative maximum or relative minimum and maximum. the next example. So let's say we have the function f of x is equal to 2x cubed minus x squared minus 7x plus 5. So the first derivative will be 6x squared minus 2x minus 7 to 0. Now, unfortunately, this equation or this quadratic equation cannot be factored. So if it is not factorable, then we have to make use of the quadratic equation. So please remember your quadratic equation, the formula negative b plus or minus square root of b squared minus 4ac all over 2a. So our b is negative 2, our a is 6, and our c is negative 7. So we have negative of negative 2 plus or minus the square of negative 2 minus 4 times a, which is 6, times c, which is negative 7 all over 2a again, which is 6. So first we square negative 2, that will be positive 4, and then multiply 4, 6, and negative 7, and then that's minus, so we get positive 168. Add them both, we get 172. 172 can be treated as the factor of 4 times 43. So again, what we do here, if we have a square root, we look for a factor that is a perfect square. So 172 has a factor 4. 4 is, of course, a perfect square. So we can extract the square root of 4. So that will become 2. And then we can factor 2 from both. We are going to factor 2 from both because we can also factor 2 from 12. And so we will have 1 plus or minus square root of 43 all over 6. So again, this is plus or minus. So that means we have actually two numbers. So we have the 1 plus square root of 43 over 6 and the 1 minus square root of 43 over 6. The first one is roughly around 1.26. And the second one is roughly negative 0.93. Why are we doing this? This is just a guide so that we can check where we are in the graph. But still, we will be using the exact value, which is the irrational number with the radical, basically. Okay, so again, the guide here will tell us which one is lesser. So the lesser number, of course, is 1 minus square root of 43 over 6. And then the bigger number is 1 plus square root of 43 over 6. So just like the second example, we have here three intervals. So we have this, second interval, and then third interval. Okay, we now go to the fourth step, which is the first derivative test. So choosing the test point was being guided by the approximation of the value. So again, 1 minus square root of 43 over 6, that was negative 0.96. So we use here the test point negative 1. Again, this is a negative number, this is a positive number, so the best test point that we can choose is 0. And then this one here, this was 1 point something, so the test point that we use is 2. So if we substitute to the first derivative, what we will get is positive. So again, substitute negative 1 to the first derivative, we get a positive. If we substitute 0 to the first derivative, we get a negative. And if we substitute 2 to the first derivative, we get a positive. So we have increasing, decreasing, increasing. To the fifth step first, we evaluate the critical points to the original equation, or the original function, I mean. So we have 1 minus square root of 43 over 6. This is cube. Remember your binomial theorem. So cube of a binomial is a cube plus 3a squared b plus 3ab squared plus b cubed. Of course, our a is 1, our b is minus square root of 43. So a cubed, that's 1 cube plus 3a squared, and then this is our b plus 3a squared. So I'm sorry, 3ab squared, that's your b squared, plus b cubed. Now for square of a binomial, that is a squared plus 2ab plus b squared. So a plus 2ab plus b squared. Okay, so evaluating the powers, of course, 1 cube is 1, 1 squared is still 1. So 3 times 1 times negative square root of 43, so that's minus 3 square root of 43. And then the square of, oh, oh yeah, the square of negative square root of 43 is 43, and then multiply it to 3, we get 129. And then the cube of negative square root of 43, that will be 43 square root of 43. Because we get a 43 square root of 43 squared times square root of 43. So the square root of 43 squared is just 43, and then multiply to square root of 43. And then, of course, 6 cubed is 216. By the way, if you have a fraction with a power, you have to apply the power to both the numerator and the denominator. That's why we have a 6 cube here. And the same thing with the square here. So we simplify, and that's the value. This one here, nothing to simplify. Then we just multiply all the coefficients, or we simplify further this one. We get 1 plus 129, that's 130. Negative 3 square root of 43 minus 43 square root of 43 is negative 46 square root of 43. And then multiply, we get those times 2. And then this one times 7. And the least common denominator of 216, 36, and 6 is 216. That is basically 36 times 6. So simplifying. So we get the final answer, 824 plus 172 square root of 43 over 216. These are all even, so we can divide them, or these are all divisible by 4. So we get 206 plus 43 square root of 43 plus all over 54, which is roughly 9.0. We'll be doing the same steps with the second critical point, 1 plus square root of 43 over 6. Um, we do the same, expand using the cube of a binomial, square of a binomial, and then redo all the same processes. So what we get here is 206 minus 43 square root of 43 all over 54, which is roughly negative 1.41. Okay, so again, what we got from the first derivative test is that it was increasing, then decreasing, then increasing. So we first have a relative maximum and then a relative minimum. So the relative maximum is, so the first critical point, 1 minus square root of 43 over 6. And then when we evaluated that into the function, what we got was 206 plus 43 over 43. 206 plus 43 square root of 43 all over 54, and the relative minimum is 1 plus square root of 43 over 6. That's the x value, and then the y value is 206 minus 43 square root of 43 all over 54. Okay, we now go to the fourth example. So let's have the function 4x cubed plus 5. So again, we find the first derivative, so that will be 12x squared equated to 0. So the only solution there is x equal to 0. So the intervals that we have is from negative infinity to 0 and 0 to positive infinity. So we will be using test points negative 1 and 1. Okay, what we have here is increasing and increasing. So it did not change from increasing to decreasing or decreasing to increasing. So we actually do not have any relative extremum. There's no maximum. There is no minimum. So if we look at the graph of 4x cubed plus 5 is actually like this. Now, please do not be confused. There is no maximum on this part. There's no minimum on this part. So it's always increasing. It just keeps on increasing. The increase here becomes a bit slight. There's slight increase, but it just keeps on increasing still. So it's always increasing. So there is no relative maximum.